morning friends, welcome to this digital lecture on HVDC, which is part of the topic in the 5th unit of the subject transmission and distribution. So while you are all holed up in your homes due to the coronavirus, right, we wanted to make this opportunity to continue the teaching learning process. Last 2 days we have been sending you notes in Google Classroom. I hope you have had an opportunity to go through the lectures, and today we want to take this process further. We are conducting classes on the digital mode, so we hope that this will be useful to you and you will benefit from this opportunity. Good morning friends, welcome to this digital lecture on transmission and distribution. Our today's topic of discussion is HVDC, high voltage direct current. So far in the previous 4 units and probably a portion of the 5th unit, we have studied transmission and distribution based on alternating current. We studied high voltage AC transmission and distribution and extra high voltage AC transmission. So today we are going to discuss the DC transmission. There has been a revival of interest in the DC transmission over the last few decades, and there are some advantages which are accruing because of this DC transmission. But still, because the existing infrastructure in a large extent is based on AC, the transition will not come all that smoothly. It will take some time. So what is it that we are gaining by DC transmission? So that is what we are going to study in detail over the next maybe 30-40 minutes. Now actually this topic is based heavily on another subject known as power electronics. But power electronics is a subject which we are studying in the 5th unit, in the 5th semester. So ideally probably the subject should have been studied after the 5th semester, but the planners of curriculum have envisaged that along with the transmission and distribution, the students should also get an overview of what this DC transmission is about. So basically we are only trying to get an overview at this point of time. Later on in an elective subject, probably in the 6th or 7th semester, we may be studying HVDC in detail along with the intricate technical aspects of power electronics. So as I said, HVDC stands for high voltage direct current transmission. Right. A question will come into your mind, if DC is going to be advantageous, why did not we start with DC transmission probably 200 years back? When electrical engineering came into being probably 200 years back, the first current, DC current, was the one which was available. There was nothing like alternating current at that point of time. Later on only was this invented, that there is a possibility of alternating current transmission, and it has got a lot of advantages. So why we initially had to go for a transition from DC to AC? This question will come to your mind. So the reason is, it is advantageous to transmit power over long distances at very high voltage. And typically your generating station, they cannot generate voltage at a very high voltage due to various manufacturing difficulties. It is difficult to probably have a generator which is insulated for 400 kV. That is simply not possible. So at the generating plant, we probably have a generator which is rated for 11 kV or maybe 22 kV, right? We don't have any generators more than probably 22 kV even anywhere in the world. So from that 11 kV or 22 kV, we need to transmit at a very high voltage. So what do? And then somebody invented this beautiful equipment called a transformer. There was a possibility that you could scale up the voltage and scale down the voltage from a small value to a very high value. So typically we have transformers which convert voltage from 11 kV to 400 kV, and at the point of consumption, again this voltage is reduced back to the required voltage, maybe 22 kV or 11 kV, or for your consumer distribution it could be 415 volts, or in a single phase 230 volts. So this equipment transformer basically works on alternating current. So we definitely needed to transmit this voltage at high voltage, and AC became very popular because of this particular requirement. So we say due to ease of transformation of voltage levels, simple transformer action. That was the reason why we initially had AC in the first place. Alternating current is universally utilized both for generation and transmission. Now we are going to say probably a little slides later that there are a lot of advantages coming from HVDC transmission, or probably even distribution at some point of time will become DC. But still we cannot do the transition suddenly because all your equipments, everything is based on alternating current still. Probably the pump which pumps water to your overhead tank, that is based on an alternating current induction motor, right? Your lighting, your fans, your mixers, grinders, every equipment is based on alternating current. So it is simply not possible that we change all this infrastructure overnight and move to DC. That will not happen. It will take a very long time, probably it will take a decade or more for this transition to take place. So generation is done at remote place away from the populated areas, that is the load center. Right? If probably generation can happen right in our campus, then we don't have this difficulty of transmitting voltage at a high voltage and stripping it down. But unfortunately that doesn't happen. Generation takes place in a place probably where you have the necessary fuel available. Suppose coal is available somewhere, it makes sense to put a coal power plant near the coal, where your availability of coal is there. So that means you generate power at one place and then you have to transmit it to your load centers, probably big cities which will be consuming power in a big way. They will be located at a far off place, we need to transmit this power. So though the power generation is done by thermal or hydel at some remote place, we have to transmit this power, and because of transformer we are able to do this at a high voltage. So turbine is working at 1525 kV, it is stepped up to 400 kV and again stepped down to our local requirement. Right, so we have several limitations of this AC transmission. We say one limitation is the line length. Right, if your transmission line is probably 100 kilometers, 300 kilometers, there is no issue. But suppose you have to transmit over, let us say, 800 kilometers. Now we have some difficulties. We say that the power which is transmitted over a particular transmitting line, we say is dependent on the sending end voltage, the receiving end voltage, and divided by the reactance of the line which is connecting these two places. Now this reactance comes into being only for alternating current. We know that for DC there is nothing like reactance, it is only a resistance. So this reactance in the denominator, that means it puts a cap. If you have a long line, this reactance is going to be higher. So there is a theoretical limit on how much you can transmit over a long line. The amount of power which you can transmit over a long line is limited by this reactance which is present in the line. And there is an additional factor known as sine of the angle between the sending end voltage and the receiving end voltage. We call that angle as delta. So sine delta is also a limiting factor. And we know that delta is 90 degrees, the sine has its maximum value, and beyond that point there is also an inherent instability in the transmission. So this is one difficulty which is the AC transmission. You have a difficulty on the line length, you have a difficulty on how much power you can transmit on the line, and we have also seen in the previous 4 units, because of this reactances in the line, there is also a drop. So as you draw power from the line, there is a lot of voltage which is getting dropped on the line. So the voltage which you receive probably is not what you expect, it is something different. And then we need to do some corrective action to bring up the voltage to the required value. So this line drops or this regulation is also an issue. And if you have a fault on the line, how are we going to sense a fault and how are we going to isolate our transmission line? Such difficulties will be there. So the advantage of HVDC is the ability to transmit large amount of power over long distance. So as we said, for DC there is no difficulty about this reactance, it is only a resistance is the only parameter which influences a DC transmission. So that you have no limitation on the length of the line. A 1000 kilometer line is also feasible. In fact, there are lines existing in Europe which connect one country from the other country. Even in India there was a proposal some time back that we will have a HVDC transmission which cuts through Pakistan, right? But probably that did not come into being because of various other reasons. So HVDC transmission allows efficient use of energy resource. So you can have energy availability in Bihar and you can run a line all the way to Chennai, right? It is possible. Such long lines are feasible. And for example, country to country, if you want to have undersea cables, yes, it is possible with the DC transmission, probably not so easy with the AC transmission. In long HVDC power transmission without intermediate taps for connecting in remote areas, right? Even in remote load centers you can connect, because you have no difficulty on the amount of power which you can transmit, right? So that way you have many other advantages which accrue from DC transmission, connecting a remote generating plant, a distribution grid. One other advantage that you can foresee, there is no issue of frequency here. When you transmit power over an alternating current mode, you need to maintain the frequency at 50 Hz. But for DC you have no such issue. You have one probably area which is having 50 Hz power, probably another area which is having 60 Hz power. No problem. In between we have a DC line, we can convert the power to DC and then reconvert it back to AC and then we can use. So we have places with the different frequencies, they can be connected together with a DC transmission. Not possible with the AC, because the AC case you have to synchronize both the ends and that is not possible if they are having different frequencies. So to facilitate power transmission between different countries, probably using different values of frequency, yes, it is possible with the DC. Reducing the line cost by way of fewer conductors and thinner conductors. Right. One major advantage which is going to come with HVDC is, we say the conductor cross section can be lesser. When you have an AC, instead of an AC you can have a DC transmission. They are going to substantiate it with some expressions which are going to say how the cost is going to reduce if you are going to have a DC transmission. So this graph will probably give you an overview how the relative cost economics works between AC and DC. Right. On the x-axis we have distance and the y-axis refers to the cost. So you have a blue line which is based on HVDC transmission and you have a red line which is based on AC transmission. So as you see, when the distances are small, then for a distance less than the break-even distance, you find that the red line is below the blue line. So the cost of AC transmission is lesser. So it doesn't make sense probably to have a DC transmission for 100 kilometers. But once you cross this break-even distance, then the DC transmission is going to be cheaper than the AC transmission and the cost economics is much more attractive. And remember, if you see at zero distance, right, at zero distance the cost is not starting from zero, it is based on a cost which is known as a terminal cost of AC over terminal cost of DC, right. In a DC, we are going to generate this direct current by converting or rectifying this alternating current to direct current. And at the point of consumption, we are going to again revert back to AC transmission. So we need two equipments in these stations. One is a rectifier which converts the AC current to DC current, and at the point of consumption, again back from the DC current into the AC current. So we are going to have huge power electronic equipments which do this job, and obviously they are still relatively expensive at this point of time. So that is why you find that the terminal cost of DC is shown to be higher, mainly because of this converter and this inverter. But beyond some point, the advantage of the transmission, the reduction in cost due to the transmission overtakes this initial terminal cost. That is why you find the DC transmission becomes more competitive beyond a particular break-even distance. Right. So as we said, there is no restriction on the line length, and the insulation value is also going to be less for a DC transmission, because for AC we know the voltage is continuously varying. What we normally refer to is the RMS voltage, but the peak voltage we know is root 2 times higher. So the insulation also has to be for root 2 times the RMS value. When you talk of DC, the voltage is constant all through. There is no difficulty about multiplying it by root 2. So you have lesser insulation cost, and the conductor cost is also going to reduce. Right. So here we have some expressions which will give you why the DC transmission is going to be less. Right. The capabilities of power transmission on an AC and DC link are different, we are going to say. Right. We are assuming some common parameters between AC and DC. We say that the insulation requirement is same. Right. So for some common parameters we are going to evaluate. So we say the insulation level is the same. The direct voltage Vd is equal to the peak voltage of the alternating current. So Vd is, let us say, the alternating voltage RMS value. Root 2 times that value is the peak value, and our DC voltage will have a magnitude root 2 times this voltage. So that means we can have a proper comparison between DC and AC. Right. On the conductor, we say that the amount of current decides the area of cross section of the conductor. And when we say RMS, we refer to the heating capability. So we say that the current is going to be the same, or the conductor cross section is also going to be the same, whether it is AC or DC, right? If you make that assumption there, so Vd is going to be root 2 times the voltage of the RMS. Current is the same, so Id is equal to Ia. Multiply by these two, you will get the power expressions. So we say for DC, the power expression gives you Vd into Id, and for AC, we say the expression comes to voltage into current into the cos phi. We know this expressions very well. So if you take the ratio of the DC power to the AC power, we obtain an expression which is root 2 divided by cos phi. Right. So if we have the same insulation, if we have the same current and consequently the same conductor size, the amount of power which you can transmit over DC and the amount of power which you can transmit over AC is a ratio root 2 divided by cos phi. Now, as we know, the maximum value of cos phi is going to be 1 unity power factor, in which case the DC transmission can transmit 1.414 times more power than the AC transmission. But 1 power factor is a very optimistic assumption. If your typical power factor is going to be only 0.8, right, then your DC transmission can probably transmit 76.8% more power than an AC transmission, which is quite attractive. right? And if you make an alternative assumption, we are only earlier we were trying to calculate the power capability. Now we assume that power is assumed to be the same. Then what happens to the conductor cross section? So probably we can choose a lower cross section for the DC. Let us evaluate how that lower cross section works out. So we say that RD is a resistance of the conductor for DC. Obviously this is going to be a smaller conductor now. RA is the cross section of the resistance of the conductor for AC transmission. For DC transmission, we say for the same amount of power, P divided by Bm, right? Because Bm is going to be equivalent to your corresponding DC value, right? So if you work out the power loss we know is I square R. So in this case, the current is given by P by Vm, right? Power divided by voltage will give you the DC current. Square of that value multiplied by RD, that will give you the power loss, right? So that works out to P by Vm whole square, and the resistance itself is given by rho L by A, our familiar expression rho L by A. A suffix D is the cross section of the conductor for DC transmission, right? The same thing when you work it out for a AC transmission, how does it work out? So the power loss, if you do the transmission by AC, right, that is given by P divided by Vm by root 2, right? Vm is your maximum value, so Vm by root 2 will give you the RMS value multiplied by cos phi. So this expression will give you the value of RMS current. So RMS current square, the RA will give you the power loss on the AC circuit. So that will work out to 2 times P by Vm whole square, and then we have this rho I divided by AA cos square phi. Expanding this expression for RA as rho L by A, right? So if you want to evaluate, if you want to compare these two, then we say the power loss is going to be the same. So P by Vm whole square rho L by A will be equal to 2 times P by Vm whole square and the expression for the resistance. Take a ratio that will give you the area of cross section for the DC over the area of cross section for the alternating current, and that comes to a value cos square phi divided by 2, right? And assuming if you have a unity power factor, then it is going to be only half. So the area of cross section for a DC conductor is just going to be half of the AC conductor, right? So earlier we said that if you assume the other things, we can transmit more power over DC. Now we are saying the reverse, that is looking at it from the other side. Assuming that for the same amount of power, we say for the area of cross section, we are going to have a much lesser conductor for DC. Even for a unity power factor, if you assume a power factor is 0.8, it is going to be much smaller. It is only going to be around 32%. So there is going to be enormous saving in the conductor cost, and that is what makes it attractive for long distance transmission, right? So we say HVDC uses less current, it has low loss, and because it is DC, we have no issue about reactances. Inductive reactance or capacitive reactance. So basically we can imagine that it is as though somebody is running on that line and without any obstruction. Whereas in AC transmission, there is a lot of obstruction on the line by way of reactances. Even if you look at the tower, probably for the AC tower, we have, let us say, a double circuit line. On the left side we have 3 conductors, on the right side we have 3 conductors, and the amount of right of space which you need for the AC tower is going to be larger. If you see the tower for a DC transmission, even at a higher voltage, 500 kV, it is more compact. You have only 2 conductors, one on the left, one on the right, and the area of land area which you are going to need is going to be less. So the cost wise is going to be less, the right of way cost is going to be less, and many times this transmission runs over long distances, over forests and so on. We are not disturbing the ecology also, because the amount of area which you are going to destroy is going to be lesser. So the towers of the DC lines we say are narrower, simpler and cheaper, right? So that is also an advantage. From the point of corona also we say DC transmission is advantageous. We have already studied corona in our second unit, right? There is some glow around the conductor on an AC transmission, and additionally we also have some power loss. For a DC transmission, that loss is going to be much less than what you have for a AC transmission. So you also have advantage by way of corona loss, right? So that gives you a background what advantages we get by way of a DC transmission. Now typically let us see how do we proceed with this DC transmission, right? So if you see this diagram here, on the left side an alternating current supply is shown, and on the right side again another alternating current is shown. It could be a supply, it could also be a load which consumes alternating current power, right? Now at today's point of time, we are still going to generate this power with AC supply only, because all our generators, they are going to generate alternating current. Basically, generator generates only alternating current. It is advantageous still to generate power by alternating current. We are only saying that transmission is going to be done by DC. We are not talking of generation. Generation is still going to be done by alternating current only. So if you have to convert it to DC, that means we need to rectify this AC supply in the first place. So we have a transformer which is shown on the left side, and then we have a rectifier there which converts this voltage into a DC voltage. So typically this transformer may convert the voltage from 11 kV to 400 kV, let us say, or maybe still higher, rectify this voltage into a DC voltage and then run this long transmission line, right? So the resistance of the line is shown as R. On the left side it is shown as UD1, and on the right side it is shown as UD2. U refers to the voltage at the left side VD1, voltage at the right side VD2. Right. So as I said, the transmission is done by DC, but we need to get the power back in an AC form. So we have to invert this power. So from the DC current, we have to again put an inverter there, convert it into alternating current, step down the voltage and give it to the various consumers. So that is what this diagram indicates. So what are the typical equipments that go into this DC transmission? Obviously the major equipment is your converter. Converting from AC to DC, it's a rectifier, or from DC to AC, which we say is an inverter, right? There is an equipment called a smoothing reactor, because probably when we study more of power electronics, we will understand the rectification process is not perfect. It is not as though you get a constant flat DC voltage. It doesn't happen like that. There are some ripples on the particular DC transmission, right? We have studied in the first semester also some experiments on rectifier. So we know that the waveform that you get on the DC side is a rippled waveform. It is a flat DC voltage. Additionally, there is also a small AC component, and we want to remove this AC component. So we have something known as a smoothing reactor, which filters out all the AC component, and what you get is only a DC voltage on the transmission, right? Additionally, some harmonics, higher order harmonics may be there on the line. We want to remove all those harmonics, so we also add something known as a harmonic filter, both at the transmission side as well as the receiving end side. Reactive power supply. Now when we talk of AC, we know that there is something known as an active power and something known as a reactive power. And for DC, we know there is nothing like a reactive power. It is only voltage into current is a power, finish, full stop, alright. There is something like VI cos phi, VI sin phi and so on. Now, we know that at the receiving end, we are still going to need AC power back. And what do we do for the reactive power at the receiving end? Because the DC transmission can only transmit active power, right? It can only transmit voltage, current, active power. So at the receiving end, probably we need another source of reactive power. So probably we need to have an equipment at the receiving end which can supply this reactive power. So typically we may have some capacitor banks at the receiving end, or if you want to limit the voltage, we probably may also have some shunt reactors, right? You also have some equipments known as electrodes which are used for earthing, actual DC line which is doing the transmission, and then for protection purpose we need to have equipments called circuit breakers. In case of any fault condition, we need to trip the line, so we have circuit breakers on the AC side. Now, tripping a DC circuit is not very easy, right? It is not as though HVDC is 100% perfect. That also has got many disadvantages, and one of the disadvantages is tripping a DC circuit is much more difficult than tripping an AC circuit, right? Because we say alternating current, by its very nature, the current starts from 0, goes to a maximum value and comes back to 0. So when we are breaking a contact, when we make a separation between a moving contact and a fixed contact, there is going to be an arc between the two contacts, and when this current comes to 0, the arc automatically is extinguished, or we need to add some additional arc quencher and we can extinguish that arc. So that advantage is available with AC, but for a DC that difficulty is there because the current will never come to 0, it is there all the time. So you are not very comfortable having a circuit breaker on the DC side, so we have circuit breakers on the AC side. On the DC side we have probably some other way of removing the current for protection purpose, right? So each of this equipment that we had an overview, converter converts the AC to DC, and then at the receiving end we have to return it back to AC, so DC to AC inverter is required. You have valves, right? The term which is used is known as valves from earlier times. After valves we had thyristors and so on. IGBTs are there, but still the old terminology is still there, so people continue to use this term valves. So transformers of course will be there. So valve bridge consists of high voltage valves in two configurations, 6 pulse and 12 pulse arrangement, right? So this is again power electronics. I will just show you a basic diagram in the next slide. So we have 6 pulse or 12 pulse circuit for each of these walls, each of these bridges. The transformers are ungrounded, so DC will be able to establish its own reference to ground. We are going to talk of 3 different ways of transmission, and we need to have our own ground on the DC side. Smoothing reactor, as I said, is going to filter out all these harmonics, and we also have harmonic filters which will trap some specific harmonics and make them zero. Reactive power supply, we said, when you need a reactive power at the receiving end, we are going to use this reactive power supply to transmit the reactive power to the load. For earthing purpose, we have these electrodes. Of course, the basic lines are there and the breakers are there to clear the faults. Right. So, what are the configurations for HVDC? We say that we have these configurations there. Major configurations: monopolar, bipolar, homopolar, and a combination multi-terminal links are also possible. Alright. So, monopolar links. This diagram is again important. On the left side, we have AC supply. On the right side, again, we have probably a load which is based on AC. So, you have a transformer and then we have a converter on the left side, and on the right side, we have the inverter. Right. So, in monopolar link, what we say is we have only one conductor. Right. We know that electricity flows only through a closed path. Over one wire, current will not flow. But here, the other wire is provided by the ground itself. Ground itself is a conductor of electricity. So, what we do is we have one single line running from the sending end to the receiving end, probably 500 kilometers long. Both at the sending end as well as at the receiving end, we do a earthing. Right? We just talked about an electrode. We do an earthing there. So, the return path is going to be through earth. Right? So, we say there's a lot of advantage because we are straight away reducing your transmission by 50%. Instead of 2 conductors, you are only having 1 conductor. There is going to be substantial saving in the cost. But it is not as though that the ground conductor is going to have zero resistance. Right? The single conductor which we are saying is probably almost zero resistance. But the earth resistance will be there. So, that way it has also got some disadvantages. So, we say monopolar link uses only 1 conductor. The return path is provided by the ground, right? Or in a C, right? Undersea transmission is also possible. The sea itself will do the conduction for the return path. So, use of the system is mainly from the cost point of view. One conductor we are straight away avoiding, so there is going to be saving. Or if I say I don't want any resistance due to earth, you can also have a metallic wire running for the return path. So, you can have a metallic return if you feel that earth resistance is too high, right? So, this we say is a monopolar link. The next possibility is we have a bipolar link, right? Left side, right side is still same. We have an AC source and then we have an AC distribution there. So, 2 converters, 1 converter to convert from AC to DC and then DC to AC, right? And we have 2 converters on the left side, 2 converters on the right side. The in-between points, if you see in the diagram, that is grounded here, right? So, if you talk of grounding there, with reference to the ground, the left side top converter will generate a positive voltage on the top line, and the left side bottom conductor will generate a negative voltage on the bottom line, right? So, that means we have 2 polarity of voltages. The top conductor will have a positive voltage, the bottom conductor will have negative voltage. Let us say positive conductor top is plus 250 kV, negative conductor is minus 250 kV, the voltage between the 2 lines is 500 kV, right? So, effectively you have a 500 kV transmission from the source to the destination, right? Additional advantage is if one converter fails, we always have to think in terms of what happens when there is a failure. So, if one circuit fails, you still have another circuit which is available, which can still provide you 50% of the power transfer capability. So, that advantage will be there with the bipolar link. So, each terminal has got 2 converters of equal rated voltage connected in series, right? Both the top and the bottom converter are connected in series. The in-between point we say is grounded. So, if one is having a fault, the other pole can continue to operate, 50% of the load can still be supplied, right? That advantage is there. Right. You also have a third possibility known as a homopolar link. Right. It has got 2 or more conductors. So here the top conductor and the bottom conductor are not having different voltages. Right. One was positive and one was negative in a bipolar. But here both are of the same polarity. The top conductor and bottom conductor are of the same polarity. And typically we use a negative polarity for this transmission. Right. It is not plus 250 kV. It is minus 250 kV on the top, minus 250 kV on the bottom, and we say there is an advantage. The corona is understood to be less for negative voltage, negative transmission. So, So corona effect in a DC transmission is less for negative polarity, so it makes sense to put the conductor at a negative voltage. So effectively we have the top and the bottom transmissions operating in parallel, right? If you see the diagram, in the previous diagram the bottom converter was having a cathode on the top, in the next diagram the cathode is on the bottom, right? So both polarities are negative, so we are able to transmit power with two voltages, both of negative polarity, and the in between point, right, that is of course your grounded point. Right, I was talking of 3 pulse rectifier and 6 pulse rectifier. So 6 pulse rectifier, the 6 pulse rectifier typical bridge configuration is shown in this diagram. In the first year lab we have studied an AC to DC rectifier. Probably you did a single phase rectifier there. This is a 3-phase rectifier because there are 3 supplies VA, VB, VC, and we have 6 thyristors connected in a configuration known as a bridge configuration, right? And we make the thyristors on in a particular sequence. We make 1 and 2 on, and after some time we make 2 and 3 on, 3 and 4. So in a particular sequence we operate the thyristors such that this output voltage V0 is always positive, right? So basically the principle is same as a single phase rectifier. We make a combination of the thyristors to conduct at any point of time such that the output voltage V0 is always going to be a positive value. So if you see the diagram there, we have 3 phases. Red is one diagram, then we have violet, and then we have green, right? So we have these 3 diagrams corresponding to the 3 supplies, R phase, Y phase and B phase. If you see the bottom diagram, right, so that is your output voltage. So the voltage goes up to a maximum value and then it starts falling. Voltage is maximum and then starts falling, and there is a net average DC voltage. So we do generate a DC voltage from this converter, but as you see it is not perfect flat DC, it is also having something known as a ripple. There is an AC component over this DC voltage, and for removing this AC component we use our smoothing reactors, right? So the current which is flowing in the converter, that is given in the bottom diagram. We have either a rectangular DC for 120 degrees or a rectangular negative minus ID for 120 degrees, and the voltage waveform is as we have just now seen, that is a waveform with a DC component but an additional AC ripple over the DC component, right? For this, now let us say we want to control a motor, a normal DC motor, we have a 6 pulse rectifier that is more than adequate for the purpose. But here when we are talking about HVDC, where we are going to talk of power in the range of 500 megawatt, 1000 megawatt transmission, right? So we want to minimize the cost at all possibilities, from all possibilities. So we say that putting a huge smoothing reactor to remove the ripple is going to be very, very expensive. So probably it is advantageous to have not a 6 pulse rectifier but a 12 pulse rectifier, right? So a 12 pulse rectifier, 12 pulse converter is obtained from 2 6 pulse converters, and the top converter and the bottom converter have a phase shift of 30 degrees. A 30-degree phase shift is given between the top and the bottom. So how do we get this phase shift of 30 degrees? That is done by an ingenious arrangement. We have a transformer. On the top we use primary star, secondary star, and for the bottom converter we say primary is star, secondary is delta. Now because of the natural phase shift between the star and delta, we get a 30-degree phase shift between the top converter and the bottom converter. So the output voltage for the top converter is again a 6 pulse output, the bottom converter is again a 6 pulse output. In series, if you combine them, you are going to have only a 30-degree phase shift, and you will get an output voltage which is having very less ripple. So the amount of filtering or the amount of smoothing reactors that you are going to need is going to be much less when you are going to use 12 pulse rectification. So invariably for all the DC, HVDC transmissions, people use a 12 pulse converter. More than 12 pulse also is feasible. Instead of 12 pulse, one could also go for 24 pulse rectifier. But then imagine you need to have 2 more converters which are going to handle large power. So the economics does not work out. So people have calculated that by and large, if you have a 12 pulse rectifier, that satisfies your ripple requirement as well as it is cost competitive, right? Now, as I said, everything is not 100% perfect. Even HVDC transmission has also got a few disadvantages. We say that the major problem is the huge cost of the converter, right? The converter is going to be rated for a very high value, so the cost is very high. Similarly, inverter is going to be a very expensive piece of equipment, and the amount of overload which these devices can withstand, that is also limited, right? Probably a thyristor or IGBT, normal current it can withstand, probably it can also withstand a 50% overload for a short time. More than that, the device may fail. So, such difficulties are also there. We also have some losses associated with this power electronic equipment, even though the efficiency is in the range of 95% and above, right? It may appear to be a very high efficiency, but think of 1000 megawatt and 5% of 1000 megawatt is 50 megawatt, right? So 50 megawatt power is going just by losses. So that is also an issue when you have very high power equipment over a DC transmission. So cost of inverter, we say to some extent it will be offset by reduction in the line cost. Of course, that is there. One more difficulty, as I said, AC circuit breaking is easy, DC circuit breaking is not all that easy. So we still don't have HVDC circuit breakers for that high voltage. We need to rely on AC circuit breakers and probably some kind of electronic control. Reliability issues are also there because you are adding equipment, you are adding converters, so any converter may fail at any time, the transmission also will be affected, right? So that in a nutshell is what we are going to, what we have seen on HVDC transmission, right? So as I said, a background in power electronics, and then probably the subject can be pursued with more depth in the coming semesters. But at this point of time, we only need to understand where HVDC scores or what difficulties that it has, right? I hope you have enjoyed this session. Thank you.